Hello, and welcome to the Worldwide Center of Mathematics. Today I'll be going over this week's Advanced Knowledge Problem of the Week. So for the full problem and the solution transcript, you can feel free to check the description of this video on our YouTube channel. So this Advanced Knowledge Problem of the Week is Thanksgiving themed, and we're really excited about it because this is a kind of fun spin on what's known as David Hilbert's paradox of the Grand Hotel. It's a paradox, it's not really, is it a paradox, is it not really a paradox? Kind of up for debate. But we're going to tackle it today, and it kind of deals with this very low level of infinity, or in fact the lowest level of infinity, countable infinities. And it's kind of this mind-blowing thing that I really enjoyed learning about when I was in high school. So we're going to tackle it together today. So you were put in charge of your Thanksgiving dinner with your family. So you had to set the table, and that seems simple, but the catch is you have an infinite number of family members. But the good thing is you have an infinitely long table with infinitely many table spots, so you set the table up so that each person has one seat, and I've put an O above each number to show that that seat has been occupied. So you fill up the entire table and everyone has a seat and you know where everyone's going to be. However, Thanksgiving rolls around and an unexpected guest comes. So the question is, can you arrange the seating so that you can fit one extra person even though it seems like every single seat is filled on that table? So that's part A. And the answer is yes, you can, because it's countably infinite. And the way you do that is you say, well, we can just make room. We can have person 1 go to the second space, have person 2 go to the next space, and so on, so forth. And for each person at seat n, you tell them to go to n plus 1. And you can kind of see that you will never run out of n's for another person to go to. So they're never going to run out of space because it's countably infinite. And when you do it like this, you'll see you just filled up a free space at the first spot because 1 went to 2, 2 went to 3, 3 went to 4, and then all the other seats are occupied. But you now have room for one extra person. And that is how you squeeze one person into a seemingly full table. That is infinite, countably infinite. And I thought that was really cool. So the second dilemma comes in part B. So part B says that a van rolls up with a countably infinite number of people. And you didn't see these people coming, so you thought your table was all full already. And the question is, can you fit a countably infinite number of people in this? And at first it seems daunting, but you're very clever, and you realize that you can tell anyone in seat n to go to seat 2n. And if you do this, then, as you can see, 1 will go to 2, 2 will go to 4, 3 will go to 6, etc. And by doing that, you free up every odd number space on your table. And it seems like you make space out of nothing, but you have to realize that this is a countably infinite number of seats. So you can just keep going on, and no n will never have a 2n to go to. And by doing that, you can tell everyone on this new van, they can just fill up the odd number spaces. And the thing is, they'll never run out of odd numbers, and your table people will never run out of even numbers, and then you will refill all the table, every single spot, all over again, and every place will be occupied, and everybody will be happy. Okay, so everything seems great. You seem to have everything under control, and then suddenly your family tells you, oh, we invited friends. We invited a lot of friends, actually. An infinite number of friends. And suddenly, your parking lot is filled with an infinite number of these infinite vans, and you don't know what to do. So, again, it seems daunting at first, but it is possible to have this done, and the key is knowing that these are countable infinities so you can count them. And the way you can do that with an infinite number of infinite vans, you can do that like this. So you basically count diagonally by taking these diagonals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And by doing that, you've grouped these into these different groups that can be then put into your table by telling person is heat n to go to n squared plus n divided by 2. So if you tell everyone to go from n to n squared plus n over 2, what that would look like is 1 would stay where they are, 2 would go to 3, 3 would go to 6, and you could have this first red person that I circled in red. They could go to seat 2. 4 and 5 could be taken by these blue people. There would be 3 for here, so that would go to 7, 8, and 9. And so on, and by doing that, you have made room in the same way that you made room before, and you managed to count out what seemed like this very impossible thing to count out. And so the last part is very similar to this one. And the entire town is interested in your party. They filled up an entire parking building filled with parking lots that are similar to this one. And I'm going to go over this one a little quicker because it's very similar, but you will see the pattern once I draw it out. And all we have to do is count it, and then we can fit a function to the people at the table, and we can make room. So, how do you count this? This is how I did it. Started with a corner, and I called that 1. I then kind of cut planes into this kind of cube. 2, 3. And you would see it looks something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And by doing that, we leave no space uncounted, and we can fit the function here. If you tell n to go to 1/6 n cubed plus 1/2 n squared plus 4/3 n, everyone would move in a way such that you can fit in these cuts in the gaps between the table, everyone perfectly. There is no space left behind. And in that, I also have solved part E in all of these examples. And that is it for this week's Advanced Knowledge Problem of the Week. We hope you enjoyed Hilbert's Paradox of the Grand Hotel. There are other ways of solving it, and we're going to encourage you to look at those other methods on their own. One that we really like is the prime factorization method, so you should definitely check that one out. So thank you very much for watching. We hope you were interested by infinity a little by this thought experiment / problem. If you want to see more Advanced Knowledge Problems of the Week, you can feel free to click up here for our playlist. If you want to subscribe to us on our YouTube channel, feel free to click right here. If you want to visit us on centermath.org, feel free to click right here. And if you're on a mobile device, there should be an eye in the corner up there. You can feel free to click that for the same links. Thank you very much for watching.